A few remarks about the homework. I start with exercise 6.3.1. You should calculate the certainty equivalent of a lottery there, and you can do it. The answer is back of the book. I tell you it's 59.922. And you see the expected value of that lottery is 60, so the certainty equivalent is a bit lower. The person prefers the expected value to the lottery, is suggesting a bit risk aversion. It can be seen, you take my word for it, that here we always, with this preference functional rank-dependent utility as the formula is written here, we always have risk aversion. For every lottery, the expected value is preferred to the lottery. Always the certainty equivalent is less than the expected value. Now, that may be a bit surprising if you look at the utility function. The utility function is a square function that is a convex function, and that suggests risk-seeking. So you see here that utility alone cannot fully determine what is happening. And indeed, in rank-dependent utility, your risk attitude, and whether you are risk-averse or not, for instance, depends both on the utility function and the probability weighting function. In general, the more concave utility is, the more risk aversion you get. And the more pessimistic, and that's convex for the probability weighting function, the more convex, pessimistic the weighting function is, the more risk aversion you get. But it can also be that one of the two brings risk-seeking and the other brings risk aversion. Then what is the overall phenomenon just depends on which of the two is the strongest effect. And often it will happen that for a few lotteries you find it suggests risk-seeking, but for a few others you get risk aversion. That is not universal. All of these kind of things can happen. But it's really the two of them. And also, if the only thing that probability weighting would do was an alternative way to give the kind of risk aversion that utility can also give, then it would not be interesting. But really, the probability weighting functions give the risk aversion of a different kind than utility. It's really a new thing. That's why the theory is worthwhile. But you also have to be watch out in this exercise. I hope you will never forget that utility alone, of course, does not determine risk attitude. Here we have a situation where you have risk aversion, but utility is not concave, utility is convex, strictly convex. That can happen. And this trivial fact signals a big misunderstanding going on in the literature in economics and even more in finance. Many people keep on saying risk aversion, that is concave utility. You know, they learned long ago when they're in their youth, their micro teacher told them risk aversion means concave utility. And that's true, unexpected utility. But it's ingrained in their brain as an absolute truth because that teacher told them. So that in other theories it may not be true, does not occur to many people. But please keep in mind, you can only say that if you assume expected utility. And now in the behavioral theories that now are getting more popular, actually, if I can choose, I'll make them more popular. Then we have, for instance, rank-dependent utility or prospect theory or other theories. Then this absolutely need not be true. So I surely hope that this exercise will help you remember and you don't forget. Now, next exercise I want to say something about is 6.6.1. There it is. That is, in fact, well, you can the answer you find at the back of the book. I will not discuss that. But you see, part A, you see exclamation mark, meaning you have to know this fact. This shows additivity of the decision weights. And then more or less, if you put the ranks the right way, you have to look a little bit. But then you see that the decision weights satisfy an additivity condition. And roughly, you have to organize the ranks such that all of them come from the same kind of lottery with the same kind of ranking of the outcomes and probabilities corresponding with it. So in a way, we have additivity of decision weights. And you will also remember that the typical novelty of rank-dependent utility was that we treat probabilities in a nonlinear manner. The probability weighting is violating the additivity condition, treat them in a nonlinear manner. And that is true, that's a novelty. But then at the level of decision weights, we have additivity. Non-additivity is only at the level of the weighting function, not at the level of decision weight, at least in this way, when this ranking is done the way it is done here. And that was a deep insight of Quiggin, a deep mathematical insight of Quiggin, that if you want to have a theory, a sensible theory, at least the only one that we've been able to think of so far, then you better maintain additivity at the level of decision weights, so weighting function differences. That was the point. It also means that the total decision weights that are assigned to a lottery, they always add to 1. And that in the old classical psychological theory, that was not so very good, that people always violate that. The total decision weight for lottery could sum to more than 1 or less than 1. And John Quiggin understood that cannot be. You don't get a sensible functional if you do that. You have to do something like this. At least that's the only thing that we've been able to think of so far to have any theory with nonlinear decision weights. And maybe new generation of researchers and maybe listeners to this may invent better theories. But at least this is how it works for the theory that we know so far. Now I go to exercise 7.4.1. I search for it. There it is. Now this exercise, again, I will not say much about the solution, but a few side remarks. This is in fact, this is a different way to measure rank-dependent utility that we will not treat much in this course. It is explained more in section 7.5. We don't have the time, but I want to say a few things that you know in the back of your mind it exists. In a way, this is dual to what we did in the experiment. Maybe you remember the first question, we measured alphas, and we saw the alphas are always equally spaced in utility units, irrespective of probability weighting function. Oh, that was nice. So then we know what the utility function is, and once we had that, we could measure the probability weighting function. That's what we did in the experiment. But here we are doing a sort of a dual thing. What we did in the experiment with utilities, here we are doing that with probability weights, so difference of probability weights as decision weights. Let us look a little bit at the structure of the preference. First, you see the lowest outcomes, which is probability 0.01 here, are always the same. And for all the difference for every I, this is the same always. And then, in a psychological sense, it always gives the same argument for going down. In an algebraic sense, if you look at the rank-dependent utility difference between the two lotteries, the two prospects, it always contributes the same term to that difference. Well then, if you want to be indifferent, the only other place where something different is happening is here, then psychologically speaking, the alpha I should be bigger than 4. This should give an argument for going up, and exactly strong enough to offset the argument for going down that we discussed before. So that's in I always want to do this homeomorphic, that the algebra fits with psychological processes. In an algebraic sense, the rank-dependent utility difference between the two prospects, this should always be contributed, for every I should be contributing the same difference to exactly offset the difference that we saw here. That's how it works. And if for every I these things give the same differences, and if you write a bit, you see that that gives you information about probability weighting. And if you do it a little bit different, but in this spirit, in section 7.5, you find equalities of decision weights, of different decision weights. And that's what you want to know to find out about the probability weighting function. So this is a dual method of measuring. Here in the experiment, we first measured the utility difference, and from that derives probability weighting. You can do it dual. And it is basically this kind of reasoning. First, you measure equalities of decision weight, so you know a lot about the weighting function. Once you know that, you can easily find the utility function. So then you know in the back of your mind that such a dual method exists, but we will not spend more time on that point in this course. We'll go on to other things. And here I finish what I wanted to say about the homework.